thanks a whole lot. It's fantastic being back here. Can you hear me now? Yes, great. I'm just here from a meeting on asteroids, comets, and meteors that was held in Japan. So I got to see the eclipse from Tokyo. And I'll be visiting with colleagues at the University of Central Florida, and then seeing my parents who live in Englewood. So this is a fantastic opportunity to come and see colleagues and family, and to meet all of you guys again. It's always great to be back here. The thing I want to talk about today is something that I find fascinating: astronomical ideas that are almost right. And by almost right, of course, I mean wrong. But wrong in interesting ways. Maybe the most famous of these ideas that were almost right is the geocentric idea of the universe. The Earth at the center and all of the planets going around the Earth, a picture we've heard about, a picture that we know Copernicus overturned. One of the things that many people don't appreciate about this system was that, in fact, it was a really good system. It lasted for 1,500 years because it did a pretty darn good job of being able to predict where the planets were going to be. You could actually go out and see the planets pretty much where you expected them to be, thanks to the mathematics of this system. But it was even more than that. It was a system that incorporated both science and art and beauty. By this system, you had all of the planets moving not because of some blind force, but because of the motions of beings that lived within the planets. Beings that were sometimes called genii. And every planet had its own genius that would then throw its demons of genius down on whoever was born then. So it figured into the astrology of the day, the philosophy of the day. It's even continued into the way we name the days of the week. The 7 planets with the sun and the moon, and then Mars and Jupiter and Mercury and Venus and Saturn. Today we have Sunday and Moon Day and Saturn Day, and the other days of the week are the Norse gods that were the equivalent. If you know your Spanish or Italian, you know the other days of the week are Mars Day and Mercury Day and Jupiter Day. The great writer C.S. Lewis, who most of us know as the guy who wrote the Narnia books, but he had a day job. He was a teacher of English literature, especially medieval literature, and he put together a series of lectures he called The Discarded Image to allow his medieval literature students to appreciate the beauty of this system that had the Earth not at the center, but at the bottom of the universe, so that all of the heavens were above it, and then we were just one level above hell itself. Few constructions of the imagination, he wrote, seem to me to have combined splendor, sobriety, and coherence to the same degree. Now, it is possible that some of you may want to point out that it did have one serious defect. It wasn't true. Aside from that, it was a glorious system. And it allowed us to make sense of the universe that we were in. One of the points of this system, of course, was not only that the Earth was at the center, but that the stars and the planets and everything revolved around the Earth. There was a brilliant mathematician in India around the year 500 who worked out the possibility that maybe the stars were fixed. Maybe the Earth was actually spinning. It was still at the center, but it was spinning, and therefore the motions of the stars that we saw was actually the motion due to the spinning of the Earth. This is 1,000 years before Copernicus. And of course, we now know he was right. Not only that, but in his writings, he worked out how long it would take for every planet to move past all of the stars and return. And the numbers that he calculated there are in that last column, the calculated periods. Now he had one problem in that, this being the year 500, the decimal point hadn't been invented yet. So the best he could do was to come up with a ratio of numbers to say, for every 125 Earth years, Mercury goes around 519 years. You do the division, and you see the numbers agree to the 5th decimal point. For every 205 Mars years, 205 Earth years, Mars goes through the sun 109 years. Again, it's good to 5 decimal points. The difference is not an error in his observations. In fact, the planetary periods are slightly different from year to year in the 5th decimal point. So what I have listed here is just the average. Phenomenally beautiful science. So why was it only almost correct? Because he didn't have the decimal point, because he was coming up with these numbers by making a ratio of 2 numbers, he assumed that the planetary periods were rational numbers, not irrational numbers. And it turns out that last decimal point makes the difference. Because if the planets were ratios, you could multiply all the ratios together to find the common denominator and work out what is the period in which all the motions of all the planets repeat themselves. The planetary positions don't repeat themselves. He was also a Hindu. He believed in a universe that repeated itself, that human activities were controlled by these demons, and if the demons repeated themselves every 4.2 billion years, which is the number he'd come up with, then he thought he had mathematical proof of a repeating universe. Brilliant science, good to 5 decimal places, almost correct. He was not the only one in the Middle Ages who realized that there was a possibility that the Earth could be moving and not the sun. Bishop Oresme writes a book on the Book of the Heavens and the Earth, 1377. In it, he just declares that all motions are relative. You know, if you had an arrow shot to the east and then to the west, the fact that they cover the same distance is not proof that the Earth is standing still, because maybe each of those arrows has its own internal natural circular motion. Absolutely right. He points out that reason alone cannot rule out the possibility that the Earth is spinning and the stars are standing still. 14th century, hundreds of years before Copernicus, and a bishop. And then he says, nevertheless, everybody knows that the Earth is standing still and the heavens are moving. What he uses is as a proof of the limits of reason. That reason alone cannot lead you to the truth, the obvious truth that the Earth is standing still. Brilliant. Almost correct. Finally, we come to the dawn of modern science and Galileo. Galileo, looking at Venus for the first time through a telescope, notices that it has a crescent shape, just like the Earth, like the moon does. And he recognizes that this is completely consistent with the Copernican view. Now, the Copernican view had been around for 70 years at this point. Nonetheless, people still, even after seeing the Copernican mathematics, which was a much more elegant mathematics, most astronomers did not believe in the Copernican system. And they didn't believe in it for very good scientific reasons. Here's the problem. If their sun is standing still and the Earth is moving, and you're looking at some nearby star compared to distant stars, at one time of the year, that star is going to appear to be in front of those guys. Half a year later, it's going to appear to be in front of those guys. Now, I've made the system, the shift, really dramatic by having the sun very close to those stars and having the fraction of that distance being a significant fraction to that distance. The farther away the stars are, the less this parallax is going to be obvious. Nonetheless, you ought to be able to see a parallax. Tycho Brahe, an astronomer in Denmark, just before the telescope, had built an observatory with a wall that was about 20 feet across, and he had it set up like a giant protractor so you could measure the position of every star and every planet moving relative to those stars to a precision of less than 10 seconds of arc. Now, from one end to the other is 180 degrees. Every degree is divided into 60 minutes. Every minute is divided into 60 seconds. This is a phenomenally high precision. And he was not able to see any parallax motion. Nonetheless, he recognized that the Copernican system did an even better job than Ptolemy and the medieval system in predicting planetary positions. So he came up with a system that allowed the Earth to be standing still, and yet all of the other planets rotated around the sun, which then in turn rotated around the Earth. And there is no observation of planets that can tell the difference between that and the Copernican system, because really they're the same system with just a different shift as to the origin point and the stars being centered on the Earth rather than the sun. A brilliant system and almost correct. Indeed, so good that other scientists contemporary with Galileo point out maybe the sun does move as Tycho supposes, and the planets make their revolutions about it while the Earth stands still. Is there not much reason for this hypothesis of Tycho when he, with all the accurateness that he arrived at with his vast instruments, or Richoli, we're going to get back to Richoli, who pretends to much outstrip him. Richoli was, of course, an Italian. This guy's an Englishman. We're not able to find any sensible parallax of the Earth's orb among the fixed stars. This is Robert Hooke, 1674. This is 30 years, 40 years after Galileo. And the evidence is still, as far as he's concerned, in favor of the Tycho Brahe system and not in favor of the Copernicus system. Robert Hooke was a great rival of Newton, and of course it's Newton's physics that finally gave the Copernican system the boost. So that was one of the reasons he didn't like Newton's idea. But there were really solid astronomical bits of evidence. Richoli is the guy who wrote this book, Jean-Baptiste Richoli of the Society of Jesus. He was a Jesuit, had an S.J. after his name, just like me. He wrote this book in 1651. Now that's less than 20 years after the infamous Galileo trial. And in this book, he makes a comparison of the Copernican system and the Tycho Brahe system. Now, you can say the Copernican system seems to be lifted up, or you could say that the Tycho Brahe system is weightier and therefore more, so that picture is kind of ambiguous. Richoli's book is famous for a number of things. One of them is it's the first map of the moon made with a telescope. Remember, this is 20 years after Galileo, that names craters with the system that we still use to this day. There are 35 names of Jesuits on the moon because the guy who made the map was a Jesuit. Very handy. Nowadays, do Jesuits have anything to do with naming craters? I'm on the IAU committee that does that. Yep. There better not be a crater guy. You have to be dead to have a crater named for you. They did make an asteroid of me, though. The most prominent crater on the moon, named by this Jesuit priest 20 years after the Galileo trial, is crater Copernicus. Right near crater Copernicus is crater Aristarchus, and crater Kepler, and crater Galileo. These are craters named for people who believed in the heliocentric system. Also in this realm is crater Richoli and Grimaldi, him and his advisor. Was he subtly saying that he also believed in the Copernican system? Some people have argued that. However, in the rest of the book, he comes up with 82 really solid scientific reasons why the Copernican system can't possibly be true. For instance, he comes up with the idea that if the Earth was spinning, you should be able to see something that we now know is the Coriolis force. And it's usually told as the reason why the swirl in the bathtub goes down one way instead of the other, which has nothing to do with that, actually. The Coriolis force is so subtle that he could not observe it at the time, but it's there. His best argument, though, is the argument of parallax, because he says, with the telescope, we can actually estimate how close stars are, and we can see stars of different distances, and we can work out that they ought to have parallax and don't. How is he able to work out the size of stars? by looking at them through a telescope and seeing how big they are. You can actually see the disk of a star in a telescope, he thinks. He's not the only one who says this. Galileo himself said this. Looking through a telescope, he sees of a disk of a star, and in the book that got him into trouble, he writes, the diameter of the sun contains the diameter of a fixed star of sixth magnitude 2,160 times. I love that high precision. So if you assume a star of sixth magnitude is equal to the sun and not larger, that amounts to saying that the sun is 1/2160th of what it now appears to be, so it's that much farther away. The distance of a fixed star of the sixth magnitude is therefore 2,160 times the distance from the sun to the Earth. What's wrong with that calculation? That calculation assumes that light goes through a hole in a perfect line like that. But in fact, light is a wave. That's not how light behaves. When light comes through a hole, like the aperture of a telescope, it actually spreads itself out. You can see that any high school physics that has a wave lab has seen how the waves spread out. Now that means that a point of light going through the opening of a telescope, like the opening of Galileo's telescope, doesn't give you just a spot, but it gives you a whole spread of light called point spread function. And any astronomer who works in astronomy with a CCD chip is familiar with these things. The light from a point appears to be spread out. Here's the trick. There's your light from a point. There's how it appears to be spread out with actually little circles around it if you've got really good optics. If you've got two stars, the fainter star with half as much light is going to be spread out that way. Now let's say you don't have perfect optics, so that the really faint part of the light down there you can't see. We wipe that out. The bright star is going to look to be wider than the faint star. And so what is actually a bright star and a dim star is going to look in your telescope as if it was a fat star and a small star. And so you're going to say, well, that star is bigger, it must be closer. Galileo makes this mistake because they didn't understand the wave nature of light, which actually Richoli and Grimaldi worked out, but they didn't work out the rest of the implications of it. So going back to what Galileo wrote, he says, if you could find some tiny star in a telescope that was really close to a big star, you ought to be able to see its motion as the Earth moves. And so it's just up to us to look for a really, really tiny star next to a really, really big star. One of these days we'll find it. One of these days we'll show that it has parallax. What he doesn't tell you is that he had already found such a star. It's in the Big Dipper. Alcor and Mizar are two stars that to the naked eye you can see are a pair of stars. But when you look at them through a telescope, there's the pair of stars, Alcor and Mizar. It turns out that Mizar is itself a double star. You can actually see in a small telescope, Galileo could see, Galileo did see, that here's a bright star and here's a dim star. We now know that that's one star orbiting the other, and they're exactly the same distance apart. He assumed that that was a close star and a distant star, far from each other. And he observed, we have it in his notebook, he observed over the course of a year to see if that star appears to move relative to that. Which, if Copernicus was right, and he was right, you ought to be able to see them move. He saw no such motion. Did that disprove the Copernicus theorem? Maybe not. He never bothered publishing it. Where did he go wrong? He assumed that stars showed disks. He assumed the size of the star disk was the size of the star. He assumed bigger stars were closer. He assumed that very close stars should show this shift in position. And when he didn't come up with the evidence he wanted, he never published it. In fact, the disks are an illusion. The size is due to the brightness, not the size. Bigger stars aren't always closer. Some stars are just brighter. Stars turn out to be so far away that the amount of parallax you see when the Earth moves is not 10 seconds of arc. It's not even 1 second of arc. A star that was 1 second of arc parallax would be a distance of what we call 1 parsec. The nearest star to us is 3.5 parsecs away, which is to say that you have to be able to measure positions to a fraction of a 60th of a 60th of a degree. And this was only done by telescopes in the 19th century. But it was eventually done. Galileo could have published this, hid it, hoping that no one would notice. Eventually, the truth comes out. Speaking of the 19th century, there was some brilliant astronomy done in the 19th century. And one of the best of the 19th century astronomers was an Italian, Schiaparelli. Schiaparelli was famous for 3 absolutely brilliant pieces of astronomy. He was the first one to really map out the surface of Mars. In his maps of the surface of Mars, which were then adopted and adapted, and the names he used are the names we still use, adopted and adapted by Percival Lowell, he sees these dark regions and he sees this brilliant series of canals. He uses the word canali, which just means channel. Percival Lowell decided those were really canals by intelligent beings. But if you compare this map of Mars with a Hubble image, you see it's actually a pretty darn good map. What's more, if you take the Hubble image, put it into Photoshop, and turn on unsharp masking to really torque up the contrast, you begin to see lines on the surface, which are, in fact, the lines that Schiaparelli was seeing. It's an optical illusion that came from his really brilliant vision, his really careful mapping of real optical illusions. Schiaparelli was the fellow who discovered the canals on Mars that aren't there. But by being a brilliant astronomer, he did more than that. He also observed the other planets, including Mercury, and he saw features in the surface of Mercury. Now, Mercury is a heck of a lot smaller than the Moon or Venus. And it's always really, really close to the Sun. So being able to see anything on Mercury is incredibly difficult. But he saw things that he thought might be canals. He saw things that he thought might be markings. By observing how those markings moved from night to night and from season to season, because he observed it over many years, he comes to the conclusion that immediately, if you're reading the part highlighted here, immediatamente e senza altre calcolone la durante la rotazione di Mercurio è uguale alla quale della sua rivoluzione siderale, cioè un giornale di 87 giorni. Immediately, and without any further calculation, you can see that the duration of the rotation of Mercury is exactly equal to that of its period around the Sun. Mercury always keeps the same face to the Sun. And this calculation is good to 1 part in 1,000, he says. And those of us who grew up reading science fiction stories by certain Mr. French, with really Isaac Asimov, know all about the idea of Mercury always keeping one side to the Sun so it was blazingly hot, and the backside of Mercury, which never saw the Sun, was freezingly cold. And this is what we all grew up with in our big golden book of astronomy. And it turns out, of course, it's not true. One of my advisors at MIT in the 1960s bounced radar waves off of Mercury and found out that the spin rate is not 88 days, but 59 days. Was Schiaparelli just a terrible observer who was seeing things in his telescope? No, it's worse than that. Mercury has a period of 88 days. The Earth has a period of 365 days. So if your Earth is here and you're looking at Mercury at its farthest distance from the sun, one 88-day period later, you can't see Mercury because the Earth has moved. Another 88-day period, and you can see Mercury again. Another 88-day period, you can't see it. So you can only see Mercury every other Mercury year. And it turns out that 59 days is exactly 2/3 of 88 days. So that Mercury has first one side facing the sun, and then one Mercury year later, when you can't see it, the other side facing the sun, and then one Mercury year later, when you can see it again, it's the same face, the first face, back again. If you look at the days when he actually observed Mercury, and you see the number of days and how many Mercury days it was always 2 Mercury days, or 4 Mercury days, or 2 Mercury days, or 4 Mercury days. It was a perfect stroboscopic event. Brilliant observation, and he made the simplest assumption, Occam's razor, which turned out to be simple and wrong. Brilliant work, almost correct. He did a third thing that many people don't know about, which to my mind is the most brilliant observation of all. I mean, if you gave me a good telescope in a dark sky, I could probably see canals on Mercury that aren't there. If you gave me a perfectly good sky and a lot of patience, I might be able to see features on Mercury every other day and be fooled the same way he does. But this third thing that he did is a kind of mathematics that, I got to confess, I'm not sure I could do. He observed meteor streams. People had seen meteor showers for many years. In particular, he looked at a meteor stream called the Leonids. Now, this is the star, and that's the constellation of Leo the lion. It looks kind of like a little lion. If you're interested in astronomy and you want to learn the constellations, get a book by H.A. Rey called The Stars, A New Way to See Them. H.A. Rey is the guy who wrote Curious George. He was a phenomenally great writer and cartoonist, and he worked out the best star book. I got it when I was in the 5th grade. I still use it. So he's got the constellation of Leo. It looks like a lion. You take away the lines, and you can see, yep, there's the stars there. And this is a meteor shower where everything seems to be coming out of the lion. This constellation shower, or this meteor shower, is called the Leonids. Not because the meteors are actually in Leo, but if you trace them back, they all seem to be tracing back to the same point. Now, there's a reason why. We now know as the Earth goes through the sun, it goes through a stream of dust just at the time when Leo is on the far side of that stream. What Schiaparelli did was to work out that that's what was happening, and then to work out, if that's the orbit of the dust, what is the period of the dust? What is the semi-major axis? We know that the dust is especially intense every 33¼ years, and that if we're hitting it in that part in the sky, this is the orbital elements, and it is exactly the same as the orbital elements of a well-known comet, Comet Tempel-Tuttle. We now know that every meteor stream has a comet or an asteroid associated with it. He was the first one to work this out. He was the first one to do the mathematics, to say meteor streams and comets are connected. And from this, he concluded that comets are formed by the accumulation of meteors in a meteor stream, which is exactly backwards. We now know that the dust is coming off the comet. He thought the comet was being formed by the dust. And I won't bother reading the Italian. Brilliant science and almost correct. While I'm talking about brilliant science, I want to mention a certain brilliant scientist of my acquaintance. You've all read Harry Potter. Book 4 of Harry Potter. He's doing his astronomy homework, And Hermione's checking over the homework, and she goes, Harry, the moons of Jupiter are covered with ice, not mice. And I'm hearing that, and I'm going, that's my thesis. That was my master's thesis. Harry Potter is quoting my master's thesis about Europa. This is the thesis right here. And I made thermal models. I typed the thesis cover wrong, so I had to retype it. Thermal models of icy satellites, and in this thesis, written by this guy with the long, crazy hair, it was the 70s, folks. I worked out what would happen if you had a body of ice and rock, and the ice melted, and because of the heat in the rock, and the ice would go to the surface, and there'd be a rocky core. And this was all 1975. This idea that you had a rocky core, and then an ocean, and then an ice crust. Hey, that's me. I showed you that Europa book. They invited me to be a co-author of the first chapter of that Europa book. Because of my expertise on Europa, I'm finally getting the credit for all this brilliance. Well, actually, they wanted me to write it because the first chapter is the history chapter, and what I did in 1975 is now considered ancient history. Because 1975 was before the Voyager spacecraft first gave us those beautiful pictures. It was before Pioneer gave us any kind of, it was before any spacecraft had been to Jupiter. Now, how did I know that the moons of Jupiter were made up of ice before we had any spacecraft there? I knew because my professor told me so. You know, he was the one who said, do this project, you'll get a master's thesis. How did he know? Well, there's two ways that you could know that the moons of Jupiter were covered with ice. The first is that they're a whole lot brighter. The moon itself only reflects 12% of the light that hits it, but Europa reflects 64% of the light that hits it. It's made out of something that's really, really bright. In addition, we know how big the moon is, and we know how massive the moon is, so you can work out the density, just as, you know, when you go to the Christmas tree and you pick up a box. When I was a little kid, we were allowed to open one present before we went off to Mass on Christmas morning. So you always wanted to make sure it was a good present. You know, you didn't want to waste your present on a box of socks. So you pick up the box and you'd feel it, and you'd feel the heft, and you go, no, this might be a book or chocolate. Either way, you win. That's called density. Density tells you what's inside a moon. By knowing the mass and knowing the volume, you know the density, and the density of the moons of Jupiter are significantly lower than the density of rock. And the only massive stuff out there that, you know, is really common is water ice. So you knew just from the density and the surface brightness that they were rich. Well, I knew that. My advisor knew that in 1971. How did he know that? Who was the first person to work that out? For this chapter in the book, I gave myself the task. Find out who was the first person who knew that the moons of Jupiter were made of water. At the Vatican Observatory, we've got this phenomenal library. The Vatican gave us, you know, all the modern books on astronomy in the Vatican Library. Modern means printed with a printing press. So I was able to go in and do some research. All right, you need to know what was the mass. How do we know the masses of satellites are actually really tough? It turns out that this Frenchman in 1803 had worked out the mathematics from mutual events of all of the masses of the moons of Jupiter, and he got them pretty darn good. Now, they're only masses relative to the mass of Jupiter itself, so you need big G for those of you in the audience who are physicists. When was big G measured? Cavendish, 1795. So, they knew the masses of these moons by 1803. How do you measure the size of the moon? You can look at it in a telescope, but they're really tiny, not much more than a dot of light. But if you notice how long it takes for the moon to disappear behind Jupiter and then come out again the other side, or the shadow of one to cross the shadow of the other, by doing that timing, you can measure the size of the moon to a very high precision. This not only gives you the volume, but it also tells you how big the moon is, so if you measure how much light is coming to you, you know the brightness, the albedo, the surface reflectance. You know, a certain brightness, is it because it was tiny but white, or really big but dark? By knowing the volume and knowing the size, you've got this measure. And this was all known by the 1840s. So they should have known by the 1840s that the moons of Jupiter were made of ice and rock. Now it's just a matter of going to some books from the 1840s and see who does this calculation. Almost nobody. Almost nobody. Simon Newcomb was one of the great astronomers, one of the great scientists. He was the Carl Sagan of his day. He was the most brilliant. He was the epitome of brilliant science. He wrote a famous paper on the orbit of an asteroid. He wrote, anybody here see the Sherlock Holmes movie that just came out? Professor Moriarty, as described by Arthur Conan Doyle, is a thinly disguised Simon Newcomb. The papers that he's supposed to have written, were actually papers written by Simon Newcomb. Now, he wasn't an evil super genius, but he was a super genius. He wrote this fabulous popular astronomy book, and in it, he writes, the light of these moons varies to an extent which is difficult to account for, except by supposing very violent changes going on in their surface. The brightness of the moons changes violently. I've seen these moons in a telescope. I've never noticed that. By the 1970s, nobody was talking about that. But here he's saying it in a book in 1850. What's going on? Then I found this book by Chambers, 1861. Of all of the books that I found in the 19th century, all of them would list the moons of Jupiter. They would list the masses of Jupiter. They would list the radii of the moons of Jupiter. So they had the volume, they had the mass. None of them calculated a density. They all had the information they needed, and nobody made the calculation, except this guy. This is the only 19th century listing I saw where he's got the mass and the volume and the density. Well, you can't see that, so let me blow it up. The density with water is equal to 1 of the moons is 0.1, 0.2, 0.3, 0.2. The moons have a density 1/10 that of water? What in nature has a density that's 1/10 the density of water? Almost nothing. Those are really strange densities. What does he have to say about these densities after he's calculated them? Nothing. One of the things that you tell your physics students after you've done the calculation, step back and ask yourself, does this make sense or did I make a mistake? He didn't do that. What's more, if I use his values for the mass and his values for the density, I come up with totally different numbers. And they're not even in error by a constant amount. Some of them are 4 times wrong and some of them are 10 times wrong. I have no idea where he goofed up, but he goofed up. And he never noticed that he goofed up. And he's the only one who even bothered to make the calculation, even though he made it wrong. Finally, at the end of the 19th century, Pickering at Harvard, this was the Harvard College Observatory in those days. In fact, right there is the office I had when I was a postdoc there. This was 100 years ago. I was a postdoc there 33 years ago, so that I don't want to go there. I'm getting to be a little historic, I'm afraid. He comes up with diameters and densities, and the densities he comes up with, and brightnesses. And the densities he comes up with are pretty much correct. Between 1 and 2 times the density of water. Rock has a density of 3 times the density of water. And brightnesses that are 30 to 40% of the light coming back, which is within a factor of 2 what the reality is. Now, one of the things he does is he actually looks at the brightness. He says, a lot of astronomers think that the light of the satellites of Jupiter is variable, but he's invented a new gizmo that brings the light of a standard star and the light of the moon into the telescope eyepiece at the same time so we can compare the two. Nobody had, because it was a very complicated set of filters and mirrors to make this happen. Before then, how did people actually determine the brightness in the telescope? You looked at it in the telescope. Then you looked at a standard star and you say, yeah, it's kind of that bright. It's a little brighter than that, not quite as bright as that. People doing that had the moons of Jupiter varying in brightness amazingly. With his system where he just had the two pieces together at the same time, they don't vary in brightness. There are a few amateur astronomers in the group here, right? Anybody figure out where everybody else had gone wrong? You're looking at Europa. You're trying to guess with your naked eye how bright Europa is. What if there's something really, really, really bright in the telescope field at the same time, like Jupiter? Your eye is going to go squirt things down. Every time Europa got close to Jupiter, it amazingly got faint. Now, before this measurement, people had come up with a completely different explanation for why it was changing brightness. They said, it's spinning really, really fast. So fast that it's squished down like a pancake. And so and then it's tumbling. So sometimes we see it edge on, and sometimes we see it face on. And he's going, no, it's actually a constant brightness. Finally, we're getting to the right answer. Then he works out the densities. The density of the moon is about 3.4. The densities of these bodies are much lower. And he concludes that they must be bright, they must be of low density, either they've got thick clouds or they're made up of heaps of white sand. Why does he say white sand? Because white sand would explain why they're so squished down. Even though he proved they didn't have to be squished down, he had disproved the evidence that they were squished down. He was so used to thinking of them as being squished down that he didn't realize he had undermined the entire idea that they were squished down. Brilliant science. Almost correct. Okay, so this is up to 1909. When did people finally understand? I look into the 20th century. All the textbooks from about 1940 onwards say, well, they're made up of ice and rock. Okay, how did they know that? One of them says, Jeffries says they're made up of ice and rock. Jeffries, who's Jeffries? I go into the literature, I look up papers by Jeffries. Harold Jeffries. In a paper in 1923, he works out the densities, and he says, obviously they're comparable to the density of ice. But his paper is actually not about the density of the moons. He's actually trying to work out what is Jupiter and Saturn made out of. And he's arguing that Jupiter and Saturn are made up of ice because they've got a density similar to ice. And besides, everybody knows the moons are made of ice, so why aren't these guys? We go from a state where nobody knew to everybody knew without him realizing that nobody knew. And he uses this correct statement to draw a completely erroneous conclusion about what Jupiter and Saturn are made of. Well, here in the technical vastness of the future, of course, we know much better. We don't make this sort of mistake anymore. Page 198 of a certain master's thesis at MIT. Given the temperatures of the interiors, and especially of the silicate layers through which the water is percolating, the possibility exists of simple organic chemistry taking place, involving either the methane from the ice or carbon in the silicates. However, we, the royal we, stop short of postulating life forms in these mantles. We leave such to others more experienced than ourselves in such speculations. So I am not the first person to predict that there was life in the oceans of Europa. I'm the first person to specifically not predict that there's life in the oceans of Europa. Who was this others more experienced than ourselves? Well, of course, I meant Carl Sagan. The very first time I presented this, my very first paper, at a meeting in 1975 at Arizona, Carl Sagan was the moderator of the session. And I come up to him and I say, I've got this great idea, life in the oceans of Europa. And he goes, Guy, what does life need to live? Food, energy. Where does life get its energy? Ultimately from the sun. You're looking at oceans that are beneath hundreds of meters, maybe hundreds of kilometers of ice. They're going to be pitch black. There's no energy source. There couldn't possibly be life there. He's right. Oh, stupid. Good thing I didn't predict life there. Boy, I would have been really foolish. 2 years later, in the deep, dark oceans of the Earth, we discover volcanoes around which life is taking the energy from the chemistry made by the volcanoes in order to make a whole series of weird forms of life where there is no sunlight. And by golly, by 1983, a bunch of authors comes up with a paper on the habitability of Europa. Second author, Stephen Squires, graduate student of Carl Sagan. Almost correct. The moral of the story. Science does make mistakes. Sometimes it takes a really long time before we correct them. Eventually we do correct them. That's one of the things that's so wonderful about science. Which means don't believe what you read in the paper is the latest version, but you probably can believe what's in some of the textbooks unless it's about the spin of Mercury. You do learn from your mistakes, if you're good. But notice the nature of a lot of the mistakes. It wasn't in the data. It wasn't in the calculation. It was in a failure of the imagination. People couldn't imagine that maybe the size of stars had to do with their brightness and not their diameter. People couldn't imagine that stars were incredibly far away. People couldn't imagine that you could have a planet made out of ice and rock. People couldn't imagine, I couldn't imagine, that you could possibly have life generated by chemistry in volcanoes rather than sunlight. So that got me thinking of imagination. And my intelligent tuna swimming here in the oceans of Europa. What if you're an intelligent tuna? The universe that you lived in would be one where there was a central body and then shells, just like the shells of the medieval universe. And if you were living in that ocean, would you ever know that there is anything beyond a universe that had a floor and a ceiling? Until maybe one day some asteroid comes, pokes a hole through the crust, rips you up into a space you never knew existed, and you discover that it's full of stars. Thanks a whole lot for coming. So we do have time for a few questions, and we've got a person with a microphone here. This is important not only so that we can hear you, but so that the YouTube version of this can also hear you. So we've got a first question over here.
In his book, Perelandra, C.S. Lewis writes about beings on another planet who had not sinned and not fallen. Mm-hmm. Would you care to speculate about that concept?
One of there are many things to talk about C.S. Lewis. You should read a book, came out about 3 years ago, called Planet Narnia, that points out that, in fact, the Narnia books are an encapsulment of the medieval universe, where every book is based on a different medieval planet. In the Perelandra books, again, he's using the medieval universe as a way of explaining, the planetary intelligences. He's telling a great story. The fact of the matter is that just as the cosmological principle maintains that the physics that we measure in our laboratories here on Earth is the same physics that you find in the distant stars, even distant galaxies, even going back to the Big Bang, I would assume that the metaphysical laws also maintain that the sign of the image and likeness of God would be intellect and free will. Any entity, no matter how many tentacles it had, that was self-aware, that knew that it existed, that knew that something else existed, and that was capable about making a choice about being in a relationship with that existence, would have the elements of what classically has been called a soul, the image and likeness of God. And if it had freedom, it would have the freedom to do things that it knew were wrong. If it doesn't have that freedom, if it can't sin, it isn't free. So I think Lewis is making an interesting storytelling point, and he's having a lot of fun with it. But I don't think even he believed that that's the way the universe actually works. Now, the question everyone always asks me is, would you baptize an extraterrestrial? And I've been asked that more times than you want to. And I get so fed up, I finally say, only if they ask. I got quoted in a British newspaper. Pope's astronomer says he would baptize extraterrestrials. Of course, the real question is not would you baptize an extraterrestrial, but would you ordain an extraterrestrial? But that's a wholly different issue. Only if they ask. Other questions? Yeah.
My understanding is that Pluto has been downgraded from a planet, but I also have heard that there's musings that there still may be an additional planet existing, and that they've observed movements in the asteroids and space junk. I'm a novice. That would indicate that they're not that gravitational influences from something they haven't seen yet.
Right.
Would you please comment?
Okay, first of all, the definition of Pluto was made by the International Astronomical Union, a collection of scientists representing different nations. And involved in that was the commission of planetary scientists, including the commission in charge of planets and moons. And the president of that commission sat on the original panel, and that happened to be me. So I was part of that panel. The definition was actually written by Chris Corbally, who was on the definition writing committee, who was another Jesuit at the Vatican Observatory. So the entire thing is a Vatican plot. Secondly, to say Pluto is downgraded is totally inaccurate. Pluto was discovered to be the perfect example of an entire class of bodies in our solar system that we never knew existed before. You remember the story of the ugly duckling? Pluto was the ugly duckling of the planets. It was the wrong size, it was the wrong orbit, it was the wrong shape, it didn't fit in. All the other planets looked down on it. And then it discovered that it wasn't a planet, it was actually a beautiful swan of a totally different kind of object, and the classic example of such an object. So now it's got a family of other bodies just like it, and it's much happier having found it from. As to the possibility that there are other bodies in the solar system, there is no definitive indication. But given the state of our ignorance, there could be something as big as Mars orbiting 500 AU from the Earth, 500 times the Earth's sun distance. We would not have seen it. On the other hand, something as big as Mars out that size, according to the current definition, wouldn't count as a planet by the current definition of what a planet is. So it's mathematically complicated, but yeah, there's still a lot we have to discover. And I think one of the most exciting things about the Pluto controversy is to remind all of us kids, we say talking to the kids, but we're all kids, to remind us that we don't have it all figured out. We're still doing an inventory of what's in our solar system. And the only thing that would be surprising is if we weren't surprised.
Brother Guy, we've got time for one more question.
Okay, one more. And I see a fellow in the front who got his hand up fast.
Can you stop yourself from not speculating for the purpose of this audience and perhaps tell us your opinion about where God fits in this? Typically, the thing that we're served is, on the one hand, there is God, on the other hand, there is science,
right.
And they coexist sort of like they exist in a typical organism. But can we talk about perhaps a little bit more robust interaction between the two?
Sure. I was once interviewed by a magazine. Fortunately, they came to me with the interview before they ran it. And they asked me, do you believe in God because of your science? You know, is your science what brought you to your faith? And I said, no, I don't believe in God because of my science. I believe in God for other reasons. I believe in God because of prayer. I believe in God because of experience of the way the universe works. I believe because I believe, and I'm not even sure why I believe, and sometimes it's a pain in the neck that I believe, but I believe. And there it was in black and white. I don't believe in God because of my science, says Brother Consolmagno. No, that's not what I meant. Now, the reason I believe in God is not science. The reason I believe in science is because of my God. Why do I think that the universe has explanations that I can find? That it's not just because the gods of the planetary intelligences move things. Instead, I insist that there's a law called gravity. That crops don't grow just because the goddess Ceres causes crops to grow. But no, there's biology that explains it. I believe in that because the particular God I believe in is not a nature God, but a supernatural God who was present at the beginning outside of nature, who made the universe deliberately and made it in a rational way because reason is great fun. And not only made the universe in this rational way, but made it in a beautiful way. So that if I have 5 different theories to guess which one's going to be right and I'm going to do research on, it's a good thing to say, what's the more beautiful theory? What's the more elegant theory? Because blind reason could make a reasonable universe. But it's hard to believe a blind universe could make a beautiful universe. I've seen 1,000 Hubble images. I've never seen an ugly one. So it's my belief in a rational, beautiful universe that allows me to do science, that encourages me to do science. And what my science tells me is about the personality of the Creator. Of all the ways the universe could be made, this is the way the universe is made. So my belief tells me that God made the universe. My science tells me how he did it. I don't read the Bible as a science book. I've written science books, and believe me, they're not Bibles. Science books go out of date within about 5 years. Literature doesn't go out of date. Philosophy doesn't go out of date. But science books go out of date. If you're trying to make the Bible a science book, you're saying it's going to go out of date, which is not what I want the Bible to do. The Bible is a book about God. It's a book about philosophy. It's a book about how things work together. And all of the different creation stories, there are many different creation stories throughout the Bible. All of them have one common point, that the universe is the deliberate act of a loving God who not only made the universe, but so loved the universe that he gave his only, I read that someplace, you know. So loved the world that this is a world that is to be loved, that this is a world in which the beauty and the rationality brings me closer to God, in which it's not an accident that when I plot 2 bits of data and I see a pattern, I feel that same jolt of joy that I feel in a magic moment of prayer. A universe where even an agnostic like Carl Sagan would be more dedicated to the truth than dedicated to just making his own career, because the truth is more important than Carl Sagan's income. If he believes in an abstract transcendent like truth, He's believing in the same God I believe in. He's just not putting a name to it the same way. Does that help? Thanks a whole lot for coming.